that Weil's fermions are ubiquitous in condensed matter physics because every time reversal invariant point, when you have spin orbit coupling and no inversion symmetry, is a Weil fermion. But then we argued that, of course, they don't need to be stuck at time reversal invariant points because they don't need any symmetry to exist. And we understood that through several ways, such as the Chern number of a Weil node, the monopole, the Dirac string, etc., etc., etc. So now I want to understand it through one last way, which brings you to the experimental consequence of the fact that you've got this monopole number. And that's the Fermi arcs. So basically, consider a system without any symmetry, again, no time reversal, nothing, and consider you having just one Weil in the bulk. Okay? Yes, you're right. You're right. Try this one. Better. Okay. So think of you having just one Weil fermion. This is periodic boundary conditions for now in Kx, Ky, Kx, Kz. Putting periodic boundary conditions everywhere, and I'm considering the situation where you have one Weil fermion. Now, of course, we understood last time that you can't have just one because you would have a Dirac string, which we explicitly solved, coming out of the Fermi surface around it. But there's another way of understanding you can't have just one by this argument. Okay? So if there's a Weil here, the Hamiltonian around this point is Ki sigma I, which I'm going to expand in Kx sigma x plus Kz sigma z plus Ky sigma y plus Kz sigma z. Okay? And the Weil happens at some, if you think of this K as being the origin of Kz, at some big Kz, and this is just the difference between this Kz, right? This is the degeneracy point, and this is just the difference between the big Kz and the momentum where you want to look at. So for example, right here it looks something like this. This is big Kz, at which the Weil is. I could take my origin there, but I don't want to. And this is small Kz. Okay, if I look at some small Kz. Okay, and I'm just going to rewrite this as considering this to be a parameter, Kx sigma x plus Ky sigma y plus m sigma z, where m is just Kz. And I'm going to ask, what is this Hamiltonian? Well, it's a 2D Hamiltonian that depends on some parameter m. And what are its whole conductances? It's a gapped Hamiltonian in this parameter m, because the spectrum is plus minus m squared plus kz plus kx squared plus kz squared plus ky squared, sorry. It's a gapped Hamiltonian at any m not equal to 0. Of course, m equals to 0 exactly the Weil node. So what are its whole conductances for m less than 0? Since it's a gapped Hamiltonian, I can compute the whole conductance of the occupied band. What is the whole conductance for m, or the Chern number for m equals 0, m greater than 0? What are they? So this is what Titus was also asked you. It was on that board there. So what are they? What's the whole conductance of this? This is a 2D Hamiltonian as a function of kx and ky. It depends on some parameter m. What's the whole conductance of it? Or the Chern number? 3, 4. So should we compute it? Okay, so if I can compute fxy, which is the wave function of the occupied state, so this as a function of this mass parameter, the bands look like this. It's got a valence band. I can compute the following quantity, partial kx of the wave function partial ky of the wave function minus x goes to y. Okay, minus x goes to y. This is dependent on k. And you'll find that this is m over square root of m squared plus k squared, where k squared is just kx squared plus ky squared. Okay? Now if I integrate this fxy of k over d2k, okay, which is kx, ky, up to some factor which you choose correctly, you're going to get that this is 1/2 the sine of the mass. And the way you get the sine of the mass is you notice there's the mass here and the square root of the mass squared. Okay? You pick up only the k equals 0 component. This will kind of die. Or actually, this is to the 3/2. No, it's to the half, something like this. Anyways, it's this. It's 1/2 the sine of the mass, what you get in the end. Okay? That's correct. So, this is correct. Okay? When you integrate, you get this just m over square root of m squared, which is just the sine of the mass with 1/2. Does this look familiar? Okay. So, that means that if I look below the Val node, every kz plane below the Val node, any kz constant plane below the Val node is a plane of constant mass in this parameter language and has Hall conductance what? Below and above. This is minus 1/2 and above. Okay, now these 1/2s are kind of, arbitrary in the sense that I only know what's happening around this node. So I don't know what's happening somewhere else in the Brillouin zone. So they're arbitrary in the sense that they're 1/2 with respect to some value that is happening in somewhere else in the Brillouin zone. Okay? That value has to be an odd multiple of 1/2 for reasons that we can go through. But the point is, below and above, this is minus 1/2 with respect to some value, and this is 1/2 with respect to the same value, because the only band closing that happens between kz negative and kz positive, or between m negative and m positive, is exactly the Val node. So anything else in the Brillouin zone at higher energies doesn't really change. So the only change has to come from this Val node. And this tells me that there's a change in Chern number or Hall conductance of 1 in between below and above. Okay? So that means that if below, you see 1/2 doesn't really make sense. There's a theorem that tells you that you can't have really 1/2, you can't have fractional Chern numbers in a non-interacting system. So this 1/2 is really 1/2 with respect to a set, with respect to an offset value of another 1/2. But the point is, between this plane and this plane, while you go through the Val node, there's a change in the Hall conductance of 1. Okay? So let's by just knowing this, let's revisit the following thing. Now, we're going to do we're going to redraw our Brillouin zone, except now I'm going to pick a periodic boundary condition in the y direction, a periodic boundary condition in the z direction, and open boundary conditions in the x direction. Okay? So this is open. So now I can have surface states, okay, since I open my boundary condition. Now for kz less than 0, 0 meaning this value of the Val node. So for planes below this Val node, so my Val node sits here. For planes below this Val node, let me take the Hall conductance to be 0. As I said, it's minus 1/2 with an offset. I can just pick it to be 0. And for k greater than 0, then the Hall conductance will be what? 1. So that means that below the Val node, I will have no quantum Hall effect for every kz plane below the Val node, or above the Val node, I will have a quantum Hall effect for every kz plane. Make sense? Okay, so every kz plane above the Val node has a quantum Hall effect, which means what? What has it got? If I just forget about the Val node, you just have the information that above the Val node, every kz plane has a quantum Hall effect. So let me just focus on one kz plane, okay, and ask you what for one kz plane, so at fixed kz, as a function of ky, how does the energy spectrum look? Okay. Well, this has a quantum Hall effect, right? It's a 2D plane at fixed kz. Ky is periodic boundary condition. X is open boundary condition. What does a quantum Hall effect have on one edge? A what? Yes. And how does it look? Yes. One chiral edge state on this edge, another one on the other edge. Okay? This chiral edge state has what? One Fermi point, right? It's wherever you've got your energy is one Fermi point. So in the Brillouin zone of the surface, can you guys see here? Everybody can see? No? Okay, maybe not, yeah. In the Brillouin zone of the surface, which is kz, kx, ky, sorry, here. This is the surface Brillouin zone. This is where the Val node was, say, somewhere. The moment I go away from the Val node, this open boundary conditions, I have a Fermi point at every kz, right? So I have a Fermi point at every kz, and that immediately, is the same thing as saying that this plane, as I would go, there's an open boundary condition in this direction. This is a surface state. Below the Val node, I have no chiral mode. Above the Val node, I have a chiral mode. Okay? So now, there's two things I can do with this chiral mode, right? First thing I can do is I can take it around and end it in the same Val node, if I could have just one Val node on the lattice. But that's nonsensical, because if I end it in the same Val node, it would mean that this has Hall conductance 1, and this has Hall conductance 1. So, there's no change in Hall conductance below the Val node and above the Val node. But I've just proved that there is. Right? So the only thing that makes sense is to end this Fermi arc in another Val node. Okay? And another Val node, you end it, and then these planes had Hall conductance 0, this plane has Hall conductance 1, and this plane has Hall conductance 0 again. And this is basically telling you that these two vials have exactly opposite monopole number, right? So if I was to compute the change from here to here, it would be +1. The change from here to here would be -1 in Hall conductance. You gain an edge state, you lose an edge state. So these are called Fermi arcs, and they're part of the reason why the vial physics has kind of formed a resurgence in condensed matter. They were pointed out by Ashwin a few years ago. Okay, and again, the reason why they're so neat is that they would not exist in a purely two-dimensional system. You can never have a Fermi surface that looks like this, right? The Fermi surface needs to end somewhere. It needs to be continuous. You can never have a Fermi surface that looks discontinuous. Of course, here, the Fermi surface only looks discontinuous, but the localization of these edge states, so when I have an edge state, I can ask how deeply does it go into the bulk? How deeply does it propagate into the bulk? Well, when I sit here, it doesn't propagate very deeply in the bulk, because this point in the bulk is not very close to any is not very close to any gapless point. But the moment I get closer and closer to the Val node, I get closer and closer to a gapless state, which is the Val node. And these edge or surface states become more and more delocalized in the bulk. Exactly when I touch the Val node, they mix with the node. They go through the surface. And if I was to plot, of course, the other surface, this is this other surface, the surface back here, what they would look like, there would be another Fermi arc on the other surface. So basically there's kind of a connectivity between two surfaces that you have here, and the projections of Vals on the two surfaces closer to me and on the other side of the sample give you two Fermi arcs. Okay, so it is a closed Fermi surface, but it's kind of a closed Fermi surface when you've got boundaries that goes from one surface through a Fermi arc, through the Val node, to the other surface, through another Fermi arc, to the other Val node, back onto the first surface. Okay? So that's kind of interesting. Why is this happening? What? That's very smart, I think. Okay. So, okay, so any questions about Fermi arcs? The point is this can be observed experimentally, and they have been observed experimentally. So any questions about these? Yes? Which Fermi point? That's right. You have, that's the remarkable, not remarkable thing, that's the neat thing. It doesn't matter what Fermi energy you pick. Since it's a chiral mode, okay, it's a chiral mode, you're going to cross it where you pick it. Now, of course, it's a very good point that you brought. This thing here is, I pick my Fermi energy, so I sit exactly at the Val node in the bulk. But I can choose not to do that. Okay, I can choose to pick my Fermi energy to sit here. Okay, now what happens is that now I have a Val Fermi surface, which is a sphere. I have another one here. But out of these ones, there's still a Fermi arc coming. Now, I can pick my Fermi surface to be even further, right? So there's a Val node here and here. Okay, I can pick my Fermi surface to be even further. The Fermi surfaces will get bigger, but as long as the Fermi surfaces with two Vals are disconnected in the bulk, there will be a Fermi arc coming from one and moving into the other. Does that make sense? Okay. Now, if I have this, there will be a Fermi level in a system with finite bandwidth where these two Fermi surfaces will touch. Okay? And you can see exactly where it is. It's exactly where the Vals connect. And when they touch, the Fermi arc disappears. Does that make sense? Okay, good. Okay, so now that I'm done with this, I want to go back and actually, point out that in any condensed matter system has Fermi arcs. You don't have to find Vals in them. In any condensed matter system, it will have Fermi arcs. The point is, how big are they? So any condensed matter system with time reversal symmetry. So let's say I have time reversal symmetry. We struggle to find arcs in Fermi arcs and Vals in weird materials, but if you don't have inversion symmetry, any time reversal invariant system will have Fermi arcs. Why? Well, as I said before, at time reversal invariant points, bands come in doublets. There's Kramer's theorem. So there's 8 time reversal invariant points. Okay? And around these time reversal invariant points, the Hamiltonian is k dot sigma. This is spin with time reversal. If you don't have any other symmetries, this is momentum. And the Hamiltonian looks Weylish around these time reversal invariant points. Right? It is a Weyl Hamiltonian. Now, just take a model sine ki sigma I. Okay, I goes from 1 to 3. So, if you take this Hamiltonian and now put your Fermi level somewhere at 0 here, well, what you're going to see is the following. You're going to see that there's a Weyl node with monopole charge or Chern number plus here, minus here, plus here, minus here, plus here, sorry, minus here, plus here, minus, plus. Okay, just believe me. You can do the calculation. You just need to do this. You just need to integrate the field strength. Remember, the field strength looks like Fij is epsilon ij L KL over K cubed, but with a plus or minus in front. Okay? A plus or minus depends on the signs. The Hamiltonian is K dot sigma here. Here is Kx sigma x plus Ky minus Ky sigma y plus Kz sigma z. So it changes a sign. That flip of a sign in K just flips this. Okay? All right. So if I choose a surface that looks kind of like this, for example, where these two Weyl nodes project on top of each other, then on my surface Fermi surface, so I just cut the material on some surface. Okay, I have my surface Brion zone has 4 time reversal invariant points. Okay, and I've argued that Weyls, since there's Weyls at time reversal invariant points in the bulk, they have to project to time reversal invariant points in the bulk. Do project to time reversal invariant points on the surface. It might be 2 time reversal invariant points in the bulk projecting to the same time reversal invariant point on the surface. Not it might be, it is always. But the point is, the surface also has time reversal invariant points, which are the projection of time reversal invariant points in the bulk. So they're the projection of Weyls. Okay. Now what happens when you've got Weyls? You've got Fermi arcs, right? So let's draw them. Let's draw the Weyls with a little bit of a Fermi surface, just so that it doesn't matter, just because the picture will look nicer. Okay. So how can I have Fermi arcs coming out of a Weyl and going to another Weyl, right? Well, I can have one of them being like this, for example. Okay. Is this a good Fermi arc in a time reversal invariant system? Why not? Somebody's shaking their head. Why not? So why isn't this a good Fermi arc in a time reversal invariant system? Well, time reversal has to be preserved on the surface, right? Time reversal is local. Anything on the surface has to be time reversal invariant. This is the Brion zone on the surface. Does this Fermi arc look like it's time reversal invariant? No. So this situation cannot exist, but the following situation can exist. Okay? And this is a time reversal invariant scenario. And you can always prove. Now, what would happen if how would you get 2 of them? Well, we know that one Fermi arc comes out of one Weyl node, so 2 Fermi arcs will come out of 2 Weyl nodes. So the projection of this point on the surface has to be 2 Weyl points of the same topological charge in the bulk. But that we know always happens in time reversal invariant systems because 2 time reversal invariant points project to 1 time reversal invariant surface point. Okay? So we always know, the Fermi arc pattern will be consistent. We always know that if I have a time reversal invariant system, I will have Fermi arcs, at least on some surfaces, between some of the projections of the time reversal invariant points on the surface. Now, what I drew there is highly exaggerated on physical grounds. It's perfectly fine on fundamental grounds, that's always what's supposed to happen. There's vials in every time reversal invariant system. Just tune to the Kramer's point, and you'll find them, and you'll find Fermi arcs. What's the issue there? Well, the issue there is that, for example, most time reversal invariant systems with spin splitting, so bands look something like this, okay? That situation exaggerated. In that situation, bands would look something like this, okay? So bands in a time reversal invariant system look something like this. These are the time reversal invariant points, 0 and pi, for example, 0 and pi. Okay, that situation that I drew there, this Hamiltonian, sine ki sigma I, looks like this. Okay, and if you put your Fermi level here, you'll see Fermi arcs between things in that Hamiltonian. Now, that situation is unrealistic in condensed matter system because this is the amount of spin-orbit coupling. Okay, the splitting between bands is the delta SO. So you would need the splitting between bands to actually be the bandwidth. Okay, so you need spin-orbit coupling as large as the bandwidth of the system in order to actually see them fully separated. What's more likely to happen, and always happens, is that the spin-orbit coupling term is very small and proportional to what Alexander, for example, showed. The Rashba term is k cross sigma is proportional to k, but you always have this k squared term, which is bound to take over, and it takes over quite fast. This k squared term is what causes this uptick, right? And this is quite large. This is the bandwidth term, right? So this will always win, and the situation will look like this. If the situation looks like this, imagine it in all 3 dimensions, how would the projection of the Fermi arc look? How would the projection? There's still a Weyl node here, but what will the surface projection of this Fermi surface look like? How will the Fermi surface look on a surface? How many? Crossing any line is how many points? 4? How would it look? So crossing any line is 4 points.
Like 2 concentric circles?
Thank you. Very good. Where will the Fermi arcs come from? Well, how will the Fermi arcs look? Well, there is a Weyl node here, so I know that there's a Fermi arc. Okay, they'll look like this. There's going to be small, shitty Fermi arcs coming out of this and moving here, right? So any condensed matter system that's got time reversal will have these Fermi arcs, except it's going to be kind of hard to see in most experimental situations. Okay? If you find an experimental material that has a spin-orbit coupling that controls your bandwidth, then you're golden because you're going to have Fermi arcs moving between time reversal invariant points. You're going to have huge Fermi arcs moving across the lattice, you know. So, okay. All right. So last thing that I wanted to do is, yes. Yes, you have to, yes, so you project both the Weyl nodes. So the Weyl nodes have some, the fundamental, if I have a 3D Brillouin zone, the fundamental constraint on the Weyl nodes is that all their chiralities sum up to 0. Okay? So I'll have 4 minuses and 4 pluses. That's if you, depending on which surface you choose. Right. So yeah, you could have surfaces on which you don't find anything. Like that's always the case. For example, if I have 2 Weyls like this, if I project on the surface if I have 2 Weyls which is plus and minus, if I project on a surface that looks down on them, I won't see anything. So you always have to find a surface. But there's always the case that no matter which surface you choose, 2 Weyls project onto the same time reversal invariant point. Right? Now, you have to find that you have 2 pluses and 2 minuses. So you just have to pick your surface. Right. Very good. That's a very good question. Thank you. Okay. All right, so the last thing that I wanted to do is show you how a topological insulator comes out of Weyls. both in 3 dimensions and in 4 dimensions. So in 3 dimensions, it's kind of neat, because in 3 dimensions, you can get the time reversal topological insulator out of vials. So I'm going to look at systems with time reversal. And I said that for systems without time reversal, the minimum number of vials is 2. For systems with time reversal, the minimum number of vials is how many? Why? Sorry? So there you go. So these are, so this is where I confused you a bit. So there's always 8 of them at time reversal invariant points. But if I want to get them at a non-time reversal invariant point, non-trim, like for example, have something like this, have something like this at a non-time reversal invariant point. How many of them would have to be? And the answer is 4. Okay? But 4 vials, I want 4 vials at non-time reversal invariant points. There's always going to be 8 vials at in every 8 vials times the number of bands you have. So 8 is per each 2 bands. Okay, because this is a doublet, this time reversal doublet, and there's 8 for each of them. So if you have 20 bands, you're going to have 160 in the whole system. Far away or from the Fermi level, but you will have them. But I want to find out how many you can have at non-time reversal invariant points. And the answer is the minimum number is 4. And you can understand it in the following way. And the following way is, let's start with 2 bands. This is some k away from the Brillouin zone. We just start with 2 bands. And if I put my Fermi level here, they're gapped. What's the Fermi surface if my Fermi level is here? No Fermi surface. So what's the Chern number of a Fermi surface, of the Fermi surface? 0, because I don't have any Fermi surface. So then I'm trying to make these cross. Can I make them cross like this in a vial node immediately? So I make them cross like k dot sigma. Could I make them cross like this? And why couldn't? So I can't make them cross like this. Like, why can't I? If I made them cross like this, I could, like, since this is a gap, I could put my Fermi level here, a little bit away. This is a spherical Fermi surface. What does it have around the vial? A Chern number of? Okay, so I can't go, this is 0, this is 1. We just argued that the Chern number has to be conserved. So what I'm actually going to create is this, where I create Chern number 1 vial here and Chern number -1 vial here. Okay? So at some point in the Brillouin zone, I'm going to create, in order to induce a band crossing at some point in the Brillouin zone, okay, I need to, at some point in the Brillouin zone that's not a time reversal invariant point. Time reversal invariant point, I always have vials, but they're stuck there. I can't do anything with them unless I break time reversal. So if I am at some non-time reversal invariant point and I'm trying to make 2 bands touch, I make 2 vials, plus and minus. Okay? Now these 2 vials, if I project them on the surface, if I make a surface in this direction, what will they have between them? Huh? Fermi arc. Okay? And if I have time reversal, so this is the gamma point. If I have time reversal, for every vial that exists here, I'll have another vial here, right? So for this one, I'll have one here. For this one, I'll have one at minus k. Now the only thing that I'm left with, and I'll know that these guys also have a Fermi arc between them. The only thing that I'm left with is to determine their monopole charge. What do you think it is? So what do you think this one is? Why? Same as this, but why? So this is how the monopole charges are. So plus, minus. Well, there's a projection on the surface. There's a Fermi arc here. Okay. So why are they plus and why are time reversal invariant vials of the same monopole charge? Well, we said that this Berry curvature under time reversal flips. Okay, this is just a magnetic field in momentum space. Magnetic fields flip under time reversal. And momentum also flips. So this is true. But we know that divergence of B is the monopole charge. This is like a magnetic field, right? This is the monopole charge, which is located at the Weyl node. Okay? So now it's pretty clear that when I flip B, I also flip K to minus K, and this remains constant. Yeah? Okay. So if I create these vials, then can these vials annihilate? Can I take this one and annihilate it at the origin with this one? So for example, can I make a path where I take this one and annihilate the origin with this one? Just guess. I mean, say something. No, why? Same charge. So the only thing that I can do is, there's only one path that I can take where I can create a band crossing and close it again. That wouldn't be very nice because I just haven't done anything. I want to do something non-trivial. So what I can do is, in a time reversal invariant fashion, move this guy here, or at the same time move this guy here, take a trajectory, move this guy here, move this guy here. This is the plus and the minus, this can annihilate. This is the plus and the minus, this can annihilate. But what are you left behind? So they annihilate and they gap the full system. What are you left behind with? A circular Fermi surface. There's a Fermi arc here. As I take it, this Fermi arc extends. The circular Fermi surface, where have you seen this? This is a topological insulator Fermi surface. So this just told you that the transition between a trivial insulator to a time reversal TI happens through a Weyl semi-metal phase. Okay? So it's not a critical point, it's a metallic phase, and that metallic phase is a Weyl semi-metal phase. And as we mentioned that vials come in pairs in 3 dimensions, if I just have one vial, what must that be? So I'm violating a doubling theorem. So what's the only way that I can have one vial? Surface of something that's 4-dimensional, and that's a 4D quantum Hall effect. Okay? And since we argued that vials are compatible with time reversal symmetry, in fact I find them at time reversal symmetric points, it must be that this 4D quantum Hall state is also compatible with time reversal symmetry.